Okay, so here we want to return to looking at graphs of cubic functions, but starting to look at the wider variety of what can happen. So we started the topic by looking at the basic cubic, y equals x cubed, which is this shape with the point of inflection, and we can apply transformations to that to reflect it, dilate it, and translate it left, right, and up and down. However, we've also talked about that a cubic graph can be shaped like this. So now we've got enough tools to be able to deal with a cubic that might look like this. So in terms of shapes, so let's talk about a positive cubic, and by that I mean, it's probably not quite the right terminology, but by that I mean a cubic function in which the x cubed term is positive. Okay, so the shape that we could get would either be this shape with the point of inflection that we've already looked at, or this shape if x cubed is positive. One of those two things. Okay, it is actually possible to have a cubic with a point of inflection that isn't stationary, but we don't really deal with those in this course. You'd have your CAS if it looked like that. For our negative cubics, we're either going to be dealing with, so that is where the x cubed term is negative. If you imagine fully expanding things out, if the x cubed term would be negative, the graph is going to go down as we go from left to right. Okay, or it could be this kind of shape. All right, so the key thing that I want you to think about is positive cubic, we go up as we go, the shape goes up as you go from left to right, and negative cubic, the shape goes down as you go from left to right. Okay. All right, so then we want to think about, we're looking at here at graphs of cubic functions when we're given the function in factorized form. Now, we don't actually have to be given the function in factorized form, but if it's expanded out, the first thing we would try and do is factorize it. Okay. Let's just have a think before we get to sort of summarizing some conclusions. Let's just have a think about some different functions. So if you had a cubic function that was, you know, x minus 2, x plus 1, x minus 4, okay, that would be a fairly basic cubic function. Now, if you were going to find the x-intercepts for that, you would let y equal 0, and you would use your Null Factor Law that would tell you that there are x-intercepts when x equals 2, when x equals negative 1, and when x equals positive 4. Okay, so our shape would be something like negative 1, positive 2, positive 4. Okay, if we're going to have 3 x-intercepts, first of all, I think about if I were to expand this out, there'd be positive x cubed. So it's going to be positive shape. It's going to go up as we go from left to right. Okay. And the next thing I think about, so it's going to be one of these two shapes on the left here. Now, if I've got 3 x-intercepts, there's only one way that happens. It can't happen for this shape here. It's only going to happen if it's this shape here. And the only way I'm going to have 3 x-intercepts is if the x-axis goes somewhere in there. Okay. So really, I've pretty much got what I need here. Okay. My shape is going to have to come up and cut through that point, and cut through that point, and cut through that point to give me a cubic. Okay. Now, let's be clear about the fact that in a cubic function, the turning points don't happen symmetrically halfway between the x-intercepts. So please don't try to mark out a point that looks like I've got that one vaguely symmetric, and it might well be, but it's not deliberate. So don't try and, I find students sometimes try and bend the graph so it'll turn where they want it to turn. Just focus on getting a nice, smooth kind of cubic shape. At this point, we don't have the tools to be able to find where the coordinates of the turning points are unless we have our CAS with us. So we do really just want to get the shape right. So this x-intercept here would be at negative 1, this one is at positive 2, this one's at positive 4. We could let x equal 0, which would leave us with negative 2 times positive 1 times negative 4 to find that that is at positive 8. Okay, and there would be the cubic graph. Let's have a think about what would happen if we had this function, y equals, we ended up with something like this at the end of the last video. Let's say we've got that. Okay, so if we were to let y equal 0 to find the x-intercepts, we would get x equals 2 and x equals negative 3 using our Null Factor Law. So we've only got 2 x-intercepts. Again, if we were to imagine expanding this out, we would end up with positive x cubed. In fact, let's do this so we've got a slightly different example here. If we were to expand that out, that would still give us x equals 2 for the intercept, because 2 minus x equals 0 is x equals 2, gives x equals 2. But if we were to expand that out, we'd have negative x cubed. So this is going to be going down as we go from left to right. Okay, and we know we've got 2 x-intercepts. So let's go back to our shapes here. So we've decided it's going down. It's going to be one of these two shapes over here. if it's going to have two x-intercepts, it can't be this one. That's never going to have two x-intercepts. That shape is only ever going to cross the x-axis once. So it has to be this one. And then if it's going to have only two x-intercepts, there's only two possibilities of what could be happening here. The x-axis could be there, or the x-axis could be there. Okay? Now, our x-intercepts were at -3 and 2. Okay, so if it was this one, that would be -3 and that would be 2. Or if it was the other one, that would be -3 and that would be 2. Obviously, we can't change the order of the number line. So the question is, which of these two things is it? And there's a bit of a hint in what the equation looks like, and it's here. Okay, the squared factor at x equals -3 means that the graph is, it doesn't exactly, but you can think about it a bit like the graph is going to behave a bit like a parabola at that point. Whereas this factor is only to a power of 1, the graph is going to behave a bit like a linear graph at that point. So at x equals 2, the graph is going to be sort of linear looking if we look very close. Whereas at x equals -3, the graph is going to be sort of parabolic looking if we look very close. So it is going to be this one. Okay. Obviously we've got our y-axis and we can work out our y-intercept. So what we would find here is that this graph is going to have x-intercept at, we can work out the y-intercept. Let's let x equal 0, so it'll be 2 times 3 squared, so it'll be 18. So quite a big y-intercept. -3, +2. We've already decided that this tells us that we're going to, our turning point is going to, sometimes we call this, it's going to touch the x-axis or bounce on the x-axis at that x-intercept. And we decided it's going to be a negative shape, and so it's going to bounce here, have a y-intercept up here, and cut here. Let's not bend the graph to turn at the y-axis, it probably won't. That's going to be 0, 18, and that's going to be 2, 0, and that's going to be -3, 0. Okay. As I said, we don't have the tools to find the turning points that aren't on the axis just yet, but that's all we would need to draw. So when we factorize the graph, the power of the factor tells us about the shape. So in factorized form, we learn where the x-intercepts are, but also what the shape is around that x-intercept. So if it's a linear factor, in the neighbourhood of that x-intercept, the graph is going to be sort of linear in shape. Whereas if it's a quadratic factor, a squared factor, in the neighbourhood of that x-intercept, the graph is going to be a sort of parabola shape. Okay? We can extend that actually, because if we were to look at something like x minus 4 all cubed, okay, so it's going to have an x-intercept at 4, and the cube factor, that means that in the neighbourhood here, it's going to behave like a cubic. We're actually going to get a point of inflection at that point. Okay, and so you could have a quartic where it also had an x-intercept at -1, and it does something like this then. Okay. Alright, so factorized form tells us a lot about what the graph looks like. Sorry, just want to get rid of some of that excess there. About what the graph, about where the x-intercepts are, but also about the shape of the graph at those x-intercepts. So if we have a factor that is just a linear factor, x minus a to the power of 1, that tells us that there is an x-intercept when x equals a, and that at x equals a, the graph is going to be cutting through the axis at that point. Okay? Cuts the axis. Okay? If we have a squared factor, x minus a all squared, there's still an x-intercept at a, but at that x-intercept at a, we're going to be getting a turning point, or a bounce, or a touch. Okay, so it just touches or bounces on the axis. Okay, we get a sort of linear shape here, we get a sort of parabola shape here, and we can extend that, sorry, that's a, and we can extend that, as I said, to a cubic. Again, if x minus a all cubed is a factor, there's still an x-intercept when x equals a. Null Factor Law tells us x minus a all cubed equals 0, so x minus a equals 0, so x equals a. But this time, we're going to be getting a point of inflection at that point. So again, in the neighbourhood, it behaves a bit like a sort of cubic shape. We could actually extend that out if you wanted to think, you know, even further about what would happen if we had x minus a to the power of 4 as a factor. So there'd be an x-intercept at a, And at A, we would get sort of a quartic shape at this point. So we would get that more kind of flat-bottomed turning point that we got with y equals x to the power of 4. Okay. So we're going to have a point of inflection at this one, and this would be a sort of quartic shape. That sort of, flat-bottomed, more extreme parabola that we talked about at the beginning of this topic. And we could extend that out. If we had a factor to a power of 5, it would be the more extreme point of inflection, and it would just start to alternate back and forth between these two shapes, just more extreme as we increase that power. So really, if we're given a polynomial in factorized form, no matter what degree, we now should be able to sketch any polynomial. Okay. So, as I said, at this stage it's not possible to find the location of the turning points, so we don't, unless they're on the axes, so we don't need to mark those for now. We're not going to be able to do that until we have some calculus that we won't cover until second semester. And the other thing is that it should be noted that turning points of cubic graphs are not symmetrically located between the x-intercepts, as was the case for quadratics. So we don't try and draw it to make it look like it's symmetric. Okay, we just focus on getting a nice smooth cubic shape going through our various points. And we certainly can't calculate the coordinates of the turning points by using any symmetry. Alright, so let's just work through some examples. Sketch the graph of y equals x plus 1, x plus 3, 2 minus x. Okay, so it's a cubic function. If I think about expanding that out, I'm going to get negative x cubed and a whole lot of other terms, but that tells me a bit about my shape, so we're going to be sloping down as we go from left to right. If we look at finding our x-intercepts, we let y equal 0, and the Null Factor Law therefore tells us that x equals -1, x equals -3, and x equals 2 will be our 3 x-intercepts. The fact that they are all powers, just linear factors, so to a power of 1, means that each of these is going to cut through the x-axis at those points. We're going to get sort of linear behaviour at those points. Our y-intercept, we're going to let x equal 0, so we get y equals 1 times 3 times 2, and so that is 6. Okay, so we've got everything that we need. We're sloping down, we've got our x-intercepts, and we've got our y-intercept. Alright, so x-intercepts at -3 and -1 and positive 2. 1, 2, 3, so here, here, and 1, 2, here. We're going down, so we're going to cut through here, we're going to cut through here, and we're going to cut through here. 2, 0, -1, 0, -3, 0, and 0, 6. And there is our cubic graph. So they're really nice and easy if you're given them in factorized form. Alright, over the page, let's have a look at example 2. Sketch the graph of y equals x times x minus 4 all squared. Okay, if you were to expand this out, you're going to get positive x cubed. Okay, and so the graph is going to go up as we go from left to right. So it's going to start down and finish up. Our x-intercepts, we let y equal 0. It's already factorized for us. So Null Factor Law tells us either x equals 0 or x minus 4 equals 0, so x equals 4. The fact that we've got a power of 1 on that x means we're going to cut at that x-intercept. The squared here means we're going to have a touch or a bounce at that x-intercept. Okay. Our y-intercept, we let x equals 0, but actually if we're thinking a little bit already, if there's an x-intercept at 0, that is also the y-intercept. The graph is going through the origin. We're getting 0 times -4 squared, but it's just going to be 0. So our y-intercept is at the origin. We go up as we go from left to right. So we're going to come up through the origin where we're cutting through, and we're going to turn somewhere and then bounce again at 4. Again, conventionally you don't really need to mark the origin, but we haven't got much else happening here. So all x-intercepts, all y-intercepts. It's probably technically not quite enough information here because there's nothing here to say that this isn't 2 times that. So it might be a bad idea to also mark another point. Perhaps just have a look at, you know, I don't know, when x equals 1, for example. We're going to have y equals 1 times 1 minus 4 squared. So it's 1 times negative 3 squared. So it's just negative 3 squared, which is 9. So maybe we just mark a point somewhere. Gives us a sense of, you know, that it's not 2 times this or 10 times this, that it's just 1 times this. Obviously, if the graph was 2 times all of this, this would be the point 118. Okay, so that's where just having a point somewhere defines that for us. Alright, example 3. Is this the last one? No, we've got another one. Sketch the graph of y equals negative x minus 3 all cubed plus 1. Now this is not factorized. Let's be clear about what factorized means. Okay? Factorized is something times something times something, nothing else. The minute you add something on the end here, it's not factorized. Okay? So this is not factorized. This is, cast your mind back to the very first video in this topic. And I throw this in here because you need to be able to flip between the two. This is a lovely cubic in turning point form, if you like. Okay, this is going to be this kind of turning point form shape, point of inflection shape. Okay, and we can see that that negative there has reflected it, so it's actually going to go this way. Okay, so it's reflected in x-axis. That's the negative out the front there, and it has gone, it's been translated to the right by 3 and up by 1. So that means that the point of inflection is going to be at 3, 1. Okay, so we're going to have this kind of shape with its point of inflection at 3, 1. We're going to need to calculate the y-intercept and the x-intercept. Y-intercept, we let x equal 0, so we get y equals negative 3 cubed plus 1. Negative 3 cubed is negative 27, but the negative out the front means it's positive 27 plus 1. And so the y-intercept is at 28. The x-intercept will only be 1 in this case with this shape. We let y equal 0. Solving cubics, if we can solve it by rearrangement, we want to. There's only one x when you've got the cubic in this form, so don't waste time expanding things out. We just want to rearrange. I'm going to add that whole bracket onto the left-hand side, well, to both sides, so that we get positive x minus 3 cubed equals 1. We're going to take the cube root of both sides. Remember, when we take an odd root, we don't get plus minus, because the cube root of positive 1 has to be positive 1. The cube root of negative 1 would be negative 1. Alright, and then we're going to add 3 to both sides, and so x equals 4. Alright, so we've got all the information we need. We've got a big y-intercept. We've got our point of inflection at 3, 1. And so if that's 3, I've defined my scale, so 4 needs to be about here. That'll be where my x-intercept has to go. And I'll just mark a symmetrical point here just to try and get the shape sort of symmetric. And I'm just going to head up to a big y-intercept up there somewhere. Okay, so that is the point 4, 0, that is the point 3, 1, and that is the point 0, 28. And there's my cubic graph. So don't be fooled by this. It's not factorized. There's not an x-intercept at x equals 3, because when you let y equal 0, you don't get x equals negative 3, okay? It's not in a factorized form. Alright, finally, let's sketch this graph. I think it's finally, yep. Let's sketch this graph here. So it's a cubic and it's not factorized. So our first aim must be to factorize it. The only advantage of this form is that we can see the y-intercept will be at 6, because when we let x equal 0, y equals 6. So that's the best thing to calculate from this form, okay? And otherwise we're going to need to factorize, because we want to find our x-intercepts, which means we're going to try and do 0 equals 2x cubed minus 5x squared minus x plus 6, and so to solve that equation we need to factorize it, so we can use the Null Factor Law. So, no common factors to divide out or to factor out, and so we need to use our factor theorem to try and find a factor. I'm going to do p of 1 is 2 minus 5 minus 1 plus 6. 2 plus 6 is 8, minus 5 minus 1 is negative 6, so that's not 0. P of negative 1 is going to be negative 2 minus 5 plus 1 plus 6. So that's negative 7 plus 7, so that is 0. Okay, so x plus 1 is a factor. We're going to need to divide to find our other factors. So let's divide x plus 1 into 2x cubed minus 5x squared minus x plus 6. Okay, again, go back to a previous video if you want to see me go through the long division more slowly. But what do we need to multiply x by to get 2x cubed? It'll be 2x squared, multiplying 2x squared by x plus 1, and then subtracting and bringing down our next term. What do we need to multiply x by to get negative 7x squared? So that'll be negative 7x, multiplying it by x plus 1, and subtracting. Negative 1 minus minus 7 is negative 1 plus 7, so that's 6. And then bringing down our final term, what do we need to multiply x by to get 6x? That'll be 6. And so 6x plus 6 is 0. Okay, so our equation is now 0 equals x plus 1 times 2x squared minus 7x plus 6. So we need to factorize this harder quadratic. So it's factors of 12 that add up to negative 7, so it's going to be minus 3 and minus 4. So I'm going to split that middle term using those factors. 2x squared, I'm going to write it as minus 4x because that's got good factors with the 2, and minus 3x because that's got good factors with the 6, although it would work even if you sub them in the other way around. Okay, factorizing by grouping. So common factors in the first two terms are 2x, leaves us with x minus 2. And common factors in the second two terms. Now, because we want the bracket to be the same, we're going to take out negative 3, which leaves us with x minus 2. So there's that nice common factor. So we can factorize now. X minus 2 is a common factor. We take that out, and we're left with 2x minus 3. Okay, so fully factorized, we've got x-intercepts at x equals negative 1, x equals 2, and x equals 3 on 2. Each of these is a linear factor, and so we're going to be cutting the axis at each of those 3 points. Alright, so we've got our y-intercept and our x-intercepts, and the shape of the graph at each of those x-intercepts. So let's just plot things out. It was a positive cubic, wasn't it? Yep, so we're going to be going up as we go from left to right. Alright, so negative 1, positive 2, and 3 on 2 is 1.5. Actually, I might just spread those out a bit. Oh, sorry. Okay, so let's make that negative 1 be positive 1 and positive 2. So we've got intercepts at 1.5 and also at 2. I'm going to cut at all of them. We're starting down and finishing up because it's a positive cubic, goes up as we go from left to right. So I'm going to come up here, we're going to have an x-intercept somewhere there. Oh, sorry, a y-intercept somewhere there. At 0, 6. That's negative 1, 0. That's 3 on 2, 0. And that is 2, 0. And there is our cubic. Okay, so some practice in exercise 6F. Please note that your textbook makes really hard work of these graphs, and it uses things that it refers to as sign diagrams. Please ignore any mention of a sign diagram. You do not need to draw sign diagrams. Just sketch the graphs and do so like we've been doing in this video here.